Alrighty, guys, we're going to add another set of notes to our notebook. And this time we're going to talk about exponential, which is just like the pluralized word sort of for exponents. Story problems, sorry. Exponential story problems. And we are going to do that on page 88. And then we'll just have one more thing to do, and this is going to be a real short one again. So if you take a look at 88, looking here, I want you guys to notice a few things. So along the side, I tell you what each letter stands for. So let's kind of highlight these things a little bit. Red. Normally what we're looking for is our final answer Y, which represents the final amount. Sometimes we're dealing with money with exponential equations. Sometimes we're dealing with like population. But exponential equations grow really quickly, much more quickly than linear equations, because an exponent makes numbers bigger faster than just multiplication. Okay, so usually what we're looking for is what the final amount is. And so when we're reading through our story problem, we're hoping that they tell me the starting amount, like the initial amount, and whatever that is, we'll go in for A. Oops, and that's down here as well. Forgot to do it on this one, my final amount. So hopefully they'll tell me like, this is how much you start with, this is how much you begin with, and that will go in for A right here. Another value that we'll always plug in is R, and R is going to be a number that represents the rate of change. Now, typically when they give you the rate of change, they'll give it to you as a percentage, but I need to change it to a decimal. Okay, so rate of change in this case won't just be like a rise over run number. It won't be a fractional number. It's going to be a percentage that I need to change to a decimal when I put it into my equation. And then if you notice, they both have a 1 in it. The only difference here is this one is a plus and this one is a minus. And hopefully that kind of makes sense. Like if I'm growing, then I should add and get bigger, bigger, bigger. Versus this one where it's decay or decreasing, I'm subtracting because I'll get smaller, smaller, smaller. Okay, so then the only other amount I want to talk about right now is T, which represents time. Which generally when we're plugging in T for time, that's usually our variable. This is the one that's either going to stay put as T if I want the whole equation, or I'll plug in the value if they want me to find that final amount. And I think I want to make a note here too that usually time is in years. So we're going to want to be careful. So let's try a couple of those. And I know there's this other box down here, which we'll get to. That one's a little different. So starting at this first one here, the population of the United States has been increasing at an average rate of 0.91%. If the population was about, 303,146,000. Oh my God, big numbers. In 2008, predict the population for 2020, which we could kind of already know, maybe when the census comes out. But let's go through and find our values. So we want to find A, R, and T. So A, again, represents my initial amount, the starting amount, which since this story is all about population, in this case, my starting population for the year that they're talking about is that 303 super huge number. So 303,146,000. R is my rate, which is a percentage that I need to change to a decimal, which I know is a little bit confusing in this case because it's already a decimal, but it's got the percentage symbol after it. So I do need to change it still by moving the decimal 2 times. So 0.0091. Sorry, one too many zeros. And then Lastly, we want to do time, which time represents years. Now they kind of give me 2 years here. So I think we want to figure out how much time has gone by. If I want to predict the population in 2020 and it starts in 2008, I really need to put in how many years have gone by. So that would be a 12 because we're doing like 2020 minus 2008, which is 12 years. Okay. So now if we fill this all in using our equation, which again looks very much like this, it's just going to have a plus instead. We'll have y equals, because I don't know that final amount yet, that's what we're trying to figure out, 303146000, parenthesis, 1 plus, and it's plus because we're growing, like they told me it was increasing, 0.0091 to the 12th power. So we just plugged it all in. Now, if I want to find the final answer, I have to follow order of operations here. So I need to start inside parentheses and add those up. And really just 1 plus that is going to be 1.0091. Like you just smush the two together. That's pretty easy. Now that I finished what's inside parentheses, I need to do exponents next. So I really now need to do 1.0091 to the 12th power, which I cannot do that in my head. This is definitely a calculator type of problem. So we'll do 1.0091. And then I need to raise that to the 12th power. So actually the super nice thing, if you are using an iPhone, is if you turn it sideways, you can raise it to the 2nd power, the 3rd power, or any power that you want. So if I click any power that I want, and then I tell it the power and hit equals, it will give me that final answer. So 1.1148, I guess, which then needs to be multiplied to this really big number. So I did the exponent, and now I finally need to multiply. And so I like to just keep this number right here so that I don't have to round really. And then just hit times 303146000. Oh my word. 337,957,677. I don't know. It's a person. Let's just chop it off. I don't want to round. I don't want to round. That is real big. People. I wonder how close that is. Like, I wonder if census information is out. I feel like it's not. Let's try another. It is estimated that the population of the world is increasing. So that increasing word tells me that I'm going to use this formula here, but with a plus sign, at an average annual rate of 1.3%. If the 2008 population was about 6,641,000,000 people, predict the 2020 population. I'm so sorry, I got something in my mouth. So A is that initial amount, that starting amount. This story is about population. That starting population was that 6 billion. So let's do it this way. Let's kind of approximate, or not really approximate, but just change that 6 billion to 6.641 billion. Okay, just because like then at the end, whatever I get, I'll just throw a billion behind it and it'll be fine. My rate is that percentage, so that 1.3% that I need to change to a decimal. So we're going to move our decimal twice, so 0.013. And then time, again, is from 2008 to 2020, so that's 12 years again. So we have y equals our 6.641 billion, just so that we don't have to write down so many zeros. Parenthesis 1 plus 0.013, that rate, to the t power, And so just like last time, follow those order of operations. We're going to do what's in parentheses first and add those two things up, which is just going to look like them smashed together. Then I need to do the exponent. So back to my handy dandy calculator here. And I'm going to type in the 1.013 to the power that I want. So this one here, 12th power, which is 1.1677, if I round correctly. But again, I'm not really going to round because now I just need to take the number that I got and multiply it by that 6.6 billion number. So I'm going to hit times 6.641. Oh my word. So y equals 7.7544 billion people. We gained a whole nother billion. All right, let's try decay. So it's the same formula, the only difference being that I subtract. And as I look through my problem, I'm looking for like a getting smaller type of word. So for instance, Nathan bought a very fancy boat for about $125,000. Oh my word. If the boat's value depreciates, which is a fancy word for loses value, which after you buy a boat, it is going to lose value. At the rate of 15% per year, what is the value of the boat at the end of 10 years? Let's find our numbers. The initial amount of the boat was 125. The rate, that percent number is 15%. I got to change it to a decimal, so 0.15. And then this time they're actually really nice to you. They straight up tell you what is the value at the end of 10 years. So they tell you exactly what it is this time. You don't have to figure it out. It's like 10 years goes by. So when we plug this all in, we have y equals 125,000, parenthesis 1 minus, because we're depreciating, 0.15 to the 10th power. Now this time it's not quite so easy. I do have to do what's in parentheses, but like doing 1 minus 0.15 is not as simple as just adding them together. The way I usually think of it is just 100 minus 15, which is 85. And then I put the decimal on because you're getting smaller. Oop, 85 to the 10th power. But the moment I get to that exponent, again, I'm wanting to do it on my calculator. So, because that is a real big exponent. So 0.85 to the 10th power is going to get smaller because we are depreciating in value. So 0.197 basically. But again, to not round, I'm just going to leave this all here, and then we're going to multiply it by the 125,000. So after 10 years, that boat is now only worth $24,609.30. Womp womp. That lost a lot of value. Alrighty, let's try another. Olivia buys a new car that costs $32,000. The value of a car is expected to depreciate 8% each year. Find the value of Olivia's car in 6 years. So guys, that is a true thing. If you buy a brand new car, it depreciates real fast and it loses value real fast. So it's always kind of better to buy used. But we'll take that initial amount, that 3200 that I bought the car at. We're depreciating 8%. So when I change that to a decimal, that's going to be 0.08. And then find her value after 6 years. So again, they just straight up tell you how many years has gone by. So 6. So we fill it all in. Y equals 32000, parenthesis 1 minus, because we're getting smaller, 0.08 to the 6th power. And then following our order of operations, we do what's in parentheses. So again, I'm just thinking 100% minus 8% is 92%. So now we're at 0.92. But the moment I got to do that exponent, I'm like, calculator, help me, please. So I got 0.92 to the 6th power. And again, it should get smaller because we are depreciating. So 0.606. And then I just need to take that and multiply it by the 32,000. And now her car is only worth $19,403.36. And like, if you guys know about Kelley Blue Book or whatever, that's kind of what they're telling you. They're taking the average rate that cars depreciate over time and they're giving you their new value. Now, lastly, when you invest money into like a bank account or something called like a mutual fund, or sometimes a stock or a bond, we use a compound interest formula that is very similar to exponential growth, where P is still my initial amount, except for they normally call it your principal. So rather than saying like, this is how much you start with, they say the principal. I don't think it's principal, it's principal. R is still rate. T is still time. But this new letter right here, N, represents the number of times that we compound throughout the year. So usually they'll tell you, but sometimes they might tell you in sort of a sneaky way. So let's try some. Determine the value of an investment of $2,500 if it is invested at an interest rate of 5.25% compounded monthly for 4 years. So I have that principal amount or that initial amount invested, which is that 2,500. My rate is still that percentage, so 5.25 that I still need to change to a decimal. So 0.0525. The 4 years is time. And so that number of times compounded always comes right after the word compounded. So like right here where it said the word compounded monthly, they are kind of hiding it from you, but monthly happens in a year 12 times because there are 12 months in a year. So if we pop all this in to our formula, we're going to have y equals our principal amount, parentheses, 1 plus, again, because we're getting bigger, we're going to earn money here, our rate over the number of times compounded to the number of times compounded, ooh, I missed that here, times time. And both those are up in the exponent. So there's kind of a little bit more to simplify here. Like inside my parentheses, like we were doing before, I do need to add, but before I even can, I need to divide. So I'll first need to do that 0.0525 divided by 12, and then add that with my 1. So 1.004375. Now also up in my exponent, I can do that little math right there, like 12 times 4 is just 48. And so now we're really looking at the same problem that we were in the first few examples, where I now need to raise this to the 48th power, and it will get bigger, not by much, but 1.233 and some stuff. Then we're going to multiply that to our initial investment. And so now, for just investing your money, you've gained like almost $500, almost $600, really. Because initially I had 2,500, but now I have 3,082. Let's try one more. Determine the value of an investment of $100,000. So that is my principal amount. Invested at an interest rate of 5.2%, which changes to 0.052. Compounded quarterly for 12 years. So 12 years. Now this time, compounded quarterly. So how many times does a quarter happen in a year? And hopefully it's what you expect. and that is 4. There are 4 quarters in a bowl, so 4. So when we plug it all in, we'll have y equals our 100,000, parenthesis 1 plus our rate as a decimal over the number of times compounded to the number of times compounded times time. And then we follow the same steps like last time. So we're going to divide first, and that I want to divide in my calculator because decimals are scary. So 0.052 divided by 4, and then add that with the 1, so 1.013. Now my exponent, again, I can do that little multiplication right there for 48, and then I'm going to raise this to the 48th power, and then times that by the 100,000 to get my new investment amount that I now have, which is $185,888.87. Yes. All right. See you guys on the next one.